Hi, welcome to my video on the governing equations of fluid motion, fluid dynamics, get toward engineers. I will be taking you on the building blocks of fluid dynamics. The three equations I will be working out from first principles are the equation of continuity, which we know is a statement of mass conservation, then the well-known Navier-Stokes equation, which is actually Newton's second law for fluid motion, and the energy equation, which is the statement of energy conservation for fluids. So moving on, we have the equation of continuity or the continuity equation. Continuity equation. So now what we have for the continuity equation is a statement of the well-known equation of continuity mass conservation. Matter cannot be created nor destroyed. Matter cannot be created nor destroyed. Matter can only be transferred from one place to another. So if you have what we call a control volume, or just a volume here, name it V. So whatever mass would be in here, the change in mass will be change in mass in there would always be due to movements in and out of V. So in essence, we don't have any V sprouting out from anywhere, any V sprouting out from the inside. There's no creation of mass. So that's a conservation equation. So in a sense, we say that the change in mass is always due to movement in and out of V. So that is same thing. We could think of our bodies as doing that. Our bodies, if we get heavier, if you got fat, meaning you could always tell that you let yourself go by eating too much than you actually burnt out. You took in too much energy than you, but that's a statement of energy, but that's also a statement of mass also. So we could put that those are also equivalent. So same thing for fluid motion. If you had a fluid body, we said V, the only change in mass of V is only due to mass entering in or mass going out. That's what makes sense. So we have to put this in mathematical form because this is how, well, and essence why I also said these equations is that we also modern day fluid mechanics we solve using fluid software, CFD, computational fluid dynamics, and to be able to appreciate computational fluid dynamics, you have to have an understanding of the basic equations and how they work. So to do this, there are two ways to determine to derive the continuity equation. We determine it using control volumes. So I'll draw a control volume here. So here is a control volume, an arbitrary shape. And then here is fluid flowing. So here's fluid flow. This could be like a river or something. And then the control volume could be fixed. This is V. Then we could have parcels of infinitesimal area. Another thing for deriving this video is that your knowledge of calculus and integration prerequisites the knowledge of calculus, integration, and vector calculus and basic calculus. So here is a control volume where fluid moves through. The control volume could either be fixed. So that means this is like a defined region that is fixed in the fluid and fluid passes through. So fluid goes in and out. Or the control volume could move with the fluid. It could be fixed, moving with the fluid, or even fixed, or even deforming with the fluid. But the only definition, if it moves with the fluid, is that it has to contain the same fluid elements. So no matter the collection of fluids in the control volume at the start, those will be the collection of fluids at the end. So let me draw a first instance and a second instance, V, control volume. I have to make some differences between V because V could stand for volume and also velocity, and I don't want to make confusion. So I would make my velocity vector always have the arrowhead. That would really help. So from now on, this is velocity, velocity. And this V, which I will try squiggle, is volume. I would also, in the direction of the Navier equation, and this would, so this will be volume. V is volume. So this is V at 1. This is the control volume at time 1. And this is the control volume V at time 2. V at time 2. The what makes the control volume the same is that at time 1, T1, and then at T2, time 1 and 2, we have the control volume holding the same elements in. So let's take this to be a first fluid parcel at time 1. At the same time, at time 2, the same fluid parcel. Fluid parcels, the fluid elements themselves would have moved up and down. They would have deformed. This one might be here. This is another fluid parcel that was here at time. This is here at time 1. See, it's at time 2. So lots of movement within the fluid parcel, but the only requirement is that at each time they must hold the same amount of elements. So I would be using this first approach to solve. So this is the first approach. So this is the approach I'll be using for the equation of continuity, a fixed volume in which fluid moves in and out. Then the second approach I'll be using is using fluid elements themselves moving. So fluid elements. So basically, this is normally applies well to integration, integral approach. An integral approach would normally use a fixed control, but it's usually interchangeable. The integral approach normally is a fixed control, while a differential approach will use an infinitesimal element, which we see moves from time to time and goes from A to B. And both of them can be seen to be equivalent, given that for the integral approach, the collection in the control volume can be broken down to be seen to be small differential elements. As we know that integration is the opposite of differentiation and vice versa. So differential approach using an infinitesimal element to do this. So let us scroll down. So using the control volume approach. So let's start using the control volume approach. So this will be fixed control volume approach. Fixed control volume approach. I'll write CV for control volume. Let's abbreviate stuff and save time. So for a fixed control volume approach, for a fixed control volume approach, I will draw a control volume fixed in the fluid, and then we have the fluid. Fluid motion is shown to be streamlined, and as we know from fluid motion, at each point, the velocity vector is the tangent to the streamline. That makes sense. So if I pick somewhere here, the velocity vector at this point is tangent to here. So we could draw this being the velocity vector at this point here. But now, that's not what I want to use. This is a fixed portion of the control volume. I want to carve out a small area element. So I name this ds in the spirit of infinitesimal calculus. And then ds has a normal pointing out. 90 degrees, n. So the collection n could be written as the whole area elements could be written as n ds. This is meant to be the area element going out of the page, or ds, whichever one suits you, but I like nds better. Whichever one suits you. Then inside this control volume, we could show the control volume to be made up of little elements, volume elements, dv. Now these are infinitesimal elements, dv. And then in this element ds, we have fluid moving through the element. So we have fluid moving through the element, we have fluid moving tangent to the element. So at each point, we just define at that point, that area element just define the vector v. So the vector v could be coming like this, it could be coming any way. Now, from vectors, we know that these two vectors are may be parallel, or may not be parallel, may be perpendicular. So now, in a nice definition of fluid flow, if I draw ds to be this, and then the vector v to be this, we can see the two vectors are in parallel, and then this is the vector ds. So that means we have fluid moving out of the control element, or we could have the vector v ds always points out, and then we have v pointing like this. This is moving perpendicular. There's no flow out of the volume. Now we could note this, that the amount of fluid leaving could be known by how lined up these two arrows are. So we could say that when the two arrows are lined up, there's max flow out, and then when the two arrows are perpendicular, there's no flow out. Then also going to the definition of in and out, when v points in this direction, this is an inflow. When v points in the same direction with this is an outflow. So this could be written as what dot product from our vectors we know. So that means the mass flow rates through ds can be seen to be m dot equals to what? Rho times the density. So which is rho? Rho is the density. Then we have what? The dot product, v dot n ds, or as I'll write it, rho v dot ds. So this accounts for inflow and outflow from the control volume for that small patch ds. So now the net mass flow from the control volume, that is looking at all ds's and all v's. So this is like we take this ds here, which could point like this, and we could have v like this, we could have ds like this, we could have v like this. We take calculations on all of them, then we add them up. That will give you an idea of the whole control volume, of whether the fluid is going out or going in at each point. So that will be an integral over the area. So we know our area integrals. So which is a summation of the whole. So this is what it looks like. So this is the net mass flow from the control volume. So now we know that the net mass flow for the control volume is this. So now we also want to equate it to what? The time rate of change. Time rate of change of the density of the mass. Let's name it the mass. Time rate of change of the mass. So the mass here is the mass, as we said, is for all elements, for small elements, in which we assume for each constant element, so for each element that we take inside here, element dV, the mass, we assume that inside the rho density is constant throughout, and then the volume is dV. The mass could be seen to be rho delta V, and then the time rate of change would be m dot is equal to what? D dt of rho dV, which is equal to what? So the total, so this is for that element, the change of mass of that element is d dt rho dV. And the time rate of change of this is the total rate of change, the total change for the whole control volume is the volume integral of this. So, which we could write to be equal to, we could move the derivative inside. We have a constant dv. The dv does not change. It's a constant parcel of sides. It's a constant cube of sides. dx, dy, and dz. But the density inside could change. So if we move it inside, we discover that the only thing changing would be the density, the rho, the t, the v. So if we integrate this, we could also move the rho, the t out, since it is constant inside it's uniform. Whatever value of rho you get inside this cube is uniform. Whatever value of time derivative of rho you get inside the cube is also uniform. You move it out, and then you have the rho, the t of the v, which could be written as the rho dt of dx, dy, the z. Now, these are time rate of change of mass in here. We want to equate it to this. How do we do that? So now we exploit a property in vector calculus known as the divergence theorem, which states that for any vector field V, I've been using V so much. Let me use something. Let me use a vector field B. The area integral of B through a surface ds, through a closed surface ds, is equal to the volume integral of the divergence of B dV. So it's very intuitive. One of my favorite formulas in math. It's very intuitive. So using this, we could see that. Okay, let me just give you a quick interpretation of the divergence theorem. At least a quick rundown that's useful for engineers. I know mathematicians would need more rigor. Would just be for closed surface here, the net outflow from the surface would always equal the sum of the individual outflows from each element. So net outflows from each element is actually equal to the sum of the individual outflows from each element here. So when you have the small cubes in there, all outflowing, the net outflow out of the surface is equal to the sum of the individual outflows. So using this to interpret this, so the net outflow, the area integral is equal to the divergence of rho v dv. I interchange this dv and del v. So rho v dv. And then this, we told you we were working with small cubes. Integrating over these small cubes is just moving the argument of the integration out, since the quantity to be integrated is constant in here. divergence of row v is constant in here, so we could move it out. And then the v is found to be dx, dy, dz. So this is del row v dx, dy, dz. And then from the continuity equation, which actually equates the net mass from the C out from the CV to the time rate of change of mass, we would see that the net what do you call it, the net time rate of change of mass to be equal to this. So we could equate this to what? The rho, the T equals rho, the V. So why did I do that? This dx, dy, dz is, you could actually write that. So let me put that in. Dx, dy, dz, dx, dy, dz. So they both cancel. And since we are working with infinitesimal elements, these quantities are the same inside each element, to be fair. So the rho dt, or we can move it to the other side to make the general statement, which everyone knows, is equal to 0. So this is the equation of continuity written in differential element form, and I would work on the other one in the next video. Thank you. This is my first try at shooting math videos. I have lots of stuff I want to share because I really enjoy this, but if you're not, you could give me tips on how you want me to improve with the presentation. So this is my first video. From the second video, I would go through it from differential element approach, where we have an element and we follow the element. And then we could see that we'll also arrive at an equation of continuity, which looks a bit different, but it's actually the same thing. So stay tuned. Thank you.